Hi everyone. I recently spent some time in the city of Freiburg, a charming place in southwest Germany in the Black Forest. Now, this area of Switzerland, southern Germany, has historically had great thinkers and great professors and highly acclaimed universities. And I found out one of the world's top astrophysicists, Dr. Bergigina, was here. She is looked at as a world expert in how the universe works and in exoplanets. She does TED Talks and is well known in astrophysics circles.
Out there in the universe. And the Earth is just one of them. In this universe, we are really tiny. We put Earth in the center of the universe. Then we realized something wrong with it, so we put the Sun in the center of the universe. Again, it was a little mixed. We put Milky Way in the center of the universe. Not so bad. And we found out in the end that there is no center of the universe. Our planet is just a single blue dot among billions of other stars and billions of other planets. We use these plants as prototypes of photosynthetic organisms in the universe. And then we build models for alien lives, how they could look. And when we puzzled with this question, how aliens can look like, we actually find answers in the backyard. When we detect life on other planets, we will understand and learn that we are not alone, and we are not special.
I wanted to interview her, but how? I thought about it and I created an alias, David Howard from Oxford University Media Society, and created some online material supporting this front. After some well thought out, tricky and delicate emails, I got the appointment, and with the backstory that I was collecting information for young students at Oxford. As I waited in the lobby of this advanced university astrophysics centre, I could see that this was a business, with funding, hierarchy, secretaries, etc. Now, before we get into the interview, for those new to the channel, know that gravity is just a theory, and my blog in 2015 explained the errors with gravity, and that it can be explained away by density and buoyancy. This blog had over 50,000 views, with not one person debunking it. Also worth knowing is that in 1931, a book called 100 Authors Against Einstein was published in German, and is in the description. This shows 100 scientists stating Einstein was leading science into pseudo-mysticism, abstraction, and speculation. It was crushed by mainstream science. Also know of the Dunning-Kruger effect, a cognitive bias in which experts mistakenly assess their cognitive ability as greater than it is. It's related to the cognitive bias of illusory superiority, and also comes from the inability of people to recognize these experts' lack of ability. Obviously, in this interview I couldn't say what I really wanted to early on, as I didn't want her to walk out. I wanted her to cover more subjects and get more answers. So take a seat and buckle up. And this gets more interesting as it continues, and presents a big key, one the truth community has needed for a while. Okay, let's play. Yeah.
Okay. And this doesn't go to unedited somewhere. You will edit this?
Yeah,
somehow?
sure. You can swear or go to the toilet or whatever, it's fine.
Okay.
Sure. Hello, Dr. Bergigina.
Hello.
If you could just spend 1 minute or 30 seconds explaining who you are and what you've done.
Oh, yeah. So I grown up in Russia. I fell in love with astronomy, first with physics and then with astronomy. And I realized that I want to understand the universe. I cannot live on Earth without knowing what's above my head. I just felt like I need to know. I went to the university, studied astrophysics and mathematics, lots of programming, because when we were studying astronomy, we were told that astronomy is not just science by itself, it's very interdisciplinary. So to be an astronomer or astrophysicist, you need to know physics, mathematics, programming, and I must tell right now, lots of social skills.
Yeah, sure. Great. I've got a few questions for you, mainly going to go to teenagers. They're probably questions you don't hear often, or you probably heard when you were a lot younger. The first one I'm going to ask is, it is said that a spinning atmosphere has no border, there's no physical border between spinning atmosphere and the vacuum, and the atmosphere gets less pressured and becomes the vacuum of space. At what altitude would you say that the atmosphere stops spinning? So gravity, they say, pulls the air molecules to the Earth, but there's still some atmosphere molecules higher up.
Yes.
At what altitude would you say these atmospheric molecules stop spinning?
Well, this is, I would formulate this question that, yes, okay. So the atmosphere spinning and gravitation forces for molecules. These are two kind of different, let's say, forces, yeah? So the spinning allows molecules to escape, actually, at certain heights, yeah?
Okay.
So they can spin and escape at some point. They escape through collisions also. There's additional forces, they collide. So
They collide with each other, or
yeah,
with
with
parts
other.
of the vacuum?
With each other.
Okay.
So in order to understand when the atmosphere ends, kind of, yeah, not like having a sharp border, but what we call atmosphere below and no atmosphere above.
Yeah.
Actually, there's another term called exosphere.
Okay.
It's nothing to do with exoplanets.
Yeah.
It was terminology before exoplanets were discovered. It's called exosphere. So that part of the atmosphere which escapes. So below that part, the atmosphere, if it exists, it's called atmosphere.
And it's spinning.
And it's spinning. And colliding, molecules colliding. But above, they already, the density is so low that they can escape because they cannot collide. They don't collide anymore.
And what happens to those molecules of atmosphere that escape into the vacuum of outer space?
Oh, they go on a cosmic journey.
Okay, and they stop spinning with the Earth?
Yes, they don't belong to the Earth anymore.
Okay.
Yes.
Is there a set altitude, distance, where that happens?
Yes, of course. It is defined by density of the atmosphere, the gravity of the planet. But for the Earth, I have to look up. If you want me to look up, I'll look up.
No, that's fine.
I don't know that number. I know that the density falls off exponentially.
Yeah.
So I actually cannot say. I mean, we tell that the space starts approximately, let's say, at 100 kilometers, above 130 kilometers, something like this, that you can go on the orbit. I mean, this spinning means like the body spinning around the Earth means that it's orbiting Earth, yeah?
Okay.
So even if we put a satellite at 200 kilometers, it's still orbiting the Earth, even though it is not in the atmosphere. So we put satellites at thousands of kilometers above, and they're still spinning around the Earth.
They're still in low Earth orbit.
Yes.
In this model.
They're still on the orbit. They're still spinning around.
Would they still be colliding with molecules of the atmosphere?
Yes, they will. If there are, yeah.
Okay.
At that height, yes.
Okay, great.
So everything is spinning around. All the also space junk, what we call, yeah. All this.
Yeah, I've got a question on that later.
Okay, good.
Okay.
So everything is spinning, and my terminology it's orbiting. Astronomy terminology it's really orbiting the Earth at very large distances. Moon, 400,000 kilometers, is still orbiting the Earth.
And this would also collide with escaped atmospheric molecules from the Earth?
Yes, and it also collides with the escaped molecules, and not molecules in this case, but more like particles and atoms from the sun.
Okay.
Which is called solar wind.
Okay.
Yeah.
Okay.
It's like hard to, I mean, the atmosphere definition is that, okay, when the molecules can escape, the atmosphere ends. You have to look up this number, for the Earth, I don't know.
But it's kind of arbitrary and it's kind of hazy.
Yeah, exactly, it's just escaping. But this escape, it's still, they can go on orbit.
Yeah.
It doesn't mean that escape means that they cannot fall on Earth anymore, because the molecules go like this. Like they collide and they go up and down all the time, yeah? So it's like turbulence, what we call.
And the reason in mainstream astrophysics that the vacuum doesn't suck out the gas is because gravity is holding the gas to the Earth.
Yeah, exactly.
Because everywhere else in science, when there's a vacuum and gas, it equilibrates.
Yes. If you just take without gravity, yes, then they start to mix. Yes.
Okay.
Our survey said.
On to the next question. It is written in astrophysics that the rotation of the Earth is due to, we can't feel it because of constant velocity. Now, one astrophysics guy I met, he said there are two constant speeds. Let me show you this.
Yes.
A bit like this fairground ride.
Yes.
And some people I know looked at some rotation physics, and they said if you're on the edge of this, you would be experiencing acceleration and deceleration. It's only the middle point that would experience, like the wizard in the middle. The wizard would be constant velocity, but if you're on the edge, you get acceleration and deceleration because of the two constant speeds. How would you answer that?
You mean why this happens? Or
Well, surely with the rotation of the Earth, and because it's going around the sun at 66,000 miles an hour, we'd be experiencing deceleration and acceleration. So think of this fairground ride. Pick one human being. So pretend that's the Earth.
So you want to include all the velocities involved, also Earth
Just two.
rotation.
The Earth rotation on its axis, 1,000 miles an hour, and 66,000 miles an hour around the sun. If you're on the edge of this sphere, like a human being, you would surely be experiencing deceleration and acceleration.
Exactly.
How does astrophysics at your level explain that?
Well, it's gravitational forces. So one gravitational force you have towards the Earth center. So this is gravity of Earth, and that what holds Earth together. And when it rotates, you experience this acceleration on the edge of the Earth and the gravity towards the Earth. But when the Earth goes around the Sun, there is gravitational force towards the center of the Sun. So two gravitational forces produce this effect of acceleration and deceleration combination.
Bingo! Yahtzee! Is that your final answer? Our survey says.
But wouldn't that mean we're not at a constant velocity, so humans should feel the rotation of the Earth?
That is interesting.
It's an interesting one. The astrophysicist I met, he did a model showing that it should show acceleration and deceleration. So I could actually show you a video where this goes around the sun, and it shows, and even you can go onto the International Space Station, which is orbiting the Earth, and this also should be showing acceleration and deceleration due to the two constant motions, just like the fairground ride.
Right. Well,
probably need some homework.
Yeah, I need some thinking.
But it's an interesting one, yeah?
It is an interesting question, yes. We usually think, that the pull, we have to compare this acceleration to the gravitational pull.
Okay.
That I would start with, because velocity is one thing, but acceleration is the other thing. So we have to compare acceleration due to rotation to the acceleration due to gravity.
Yeah.
And it's very possible that gravitational acceleration is larger. That's why we just don't feel this side.
I think we would need three different answers. One for the Earth, one for the International Space Station, and then one, imagine an astronaut outside the International Space Station. Yes. How would he be staying with the space station? Because they're all doing this they're all acting under these two constant forces, two constant motions.
Exactly, yeah.
So this is a question I can't get answered. It's a very interesting one.
Yeah, but in this case, space station and the astronaut in space, they are like we call it probe particles, free particles to probe the gravitational field. Yeah. So they will orbit the Earth because of the gravitational pull of Earth, but together with Earth, they will move around the Sun. So, and that is because the gravitational acceleration of the Earth to the Sun is much larger than gravitational acceleration of any of us to the Earth.
So they just don't notice it?
Yeah, they don't notice this.
Okay.
So that is, I think this, of course, the rotation around the Sun, orbiting around the Sun, it's a huge velocity. But we're so pulled to the Earth that this Earth to the Sun is somewhere.
Our survey said...
Yeah. In the 1700s, on the same theme, James Bradley did an experiment which was redone in 1871 by a G. Airy. Obviously, this is a long time ago. And also the Michelson-Morley experiment in 1887. All these detected no rotation of the Earth. It's a bit of a silly question.
No, they detected no ether.
No ether. Yeah, I've read this.
Yes, no motion of the Earth with respect
to the sky.
Motionless ether. That's the measurement. So they disprove that there is ether.
Okay. Yeah, this could be interpreted in many ways. So what scientific method, instrumentation or experiment would you say proves the Earth is rotating? What would be your first, number one best proof if you were doing a lecture?
That we see sunsets and sunrises,
Okay.
moonsets and moonrises, yes.
Our survey said...
This is the first, we see sky moving, basically, yeah? So.
But, obviously back in the old days, they would say the sky's moving.
Yes.
Yeah.
So, but now we know this is if we understood that we are humans, not us. Humans are not in the center of the universe, if you take this Aristotle system, we are in the center of the universe.
It's funny because the Planck probe in 2013 did say we are the center of the universe. I don't know if you ever studied that experiment.
Yes, Planck, I don't know why they said it. It's like we're in the center. Yes, that's, I want to tell this. So
sure, okay.
Aristotle said, okay, we're in the center of the universe, Earth, and everything around rotates. Yeah. Then Galileo and Copernicus and Kepler, they said, no, the sun in the center of the universe. Yeah. Then Hubble came 100 years ago, said that, we see that all galaxies are moving away from us. Doesn't mean that we're really in the center of the universe. Yeah. But then later we found out that space expands. Einstein said that no, the galaxy is moving fine, but it's not that because we're in the center of the universe. It's because space expands at every point of the universe. So every point of the universe could be wherever you were in the universe. You would see that everything expands from you. So you would always feel I am in the center.
Let's go on to gravity. This probably come across as a very obscure question. So these people said to me, gravity is strong enough to hold boats and cargo and cars to a spinning ball, but yet it's not strong enough to pull the butterfly down or these small areas of these dead flowers. How would you answer that?
This is the buoyancy, yeah. So when it's the same question, how can we swim in water? So why don't you fall to the bottom of the swimming pool?
Buoyancy.
It's buoyancy.
But then couldn't gravity be explained away? Because gravity is a theory, yes? It's a worldwide agreed theory. It's not, I don't think anyone's got the graviton.
It's a theory, but it's very well tested and very well confirmed. Even though we don't see graviton, it's still very well tested, yes.
Could gravity be explained away with density and buoyancy?
It's not gravity. I said it's buoyancy. It's combination of buoyancy and gravity.
Back to the butterfly.
Yes.
Yeah.
So you swim in a swimming pool or ship on the water. You have two forces again. So in every physics study, this for students, they need to take all forces into account, which are essential. So in this case, one goes down, gravity, and one goes up, is buoyancy. And you can swim when on the surface. At the surface, these two forces are equal. So if you go down, gravity will be stronger, but buoyancy also will be stronger. So then you can float.
How does that affect the dead part of the flower?
It's the same. Atmosphere is the same as a swimming pool. There is atmospheric buoyancy.
Okay.
So it's the same for light creatures like butterflies and dandelion. I don't know how they call them in English.
And
how these things are called in English?
It's called a dandelion.
Yeah, the whole thing. But this one?
I don't know. There's no such word.
So they're also floating. because the buoyancy for these things is much larger than gravity. The mass is very tiny, but they are puffy. So for them, the volume is bigger than the mass. It's the mass ratio volume to mass, basically.
Okay.
So, and the volume is much bigger than the mass, and so the buoyancy is much larger than gravitation. And for the butterfly, I guess they can coordinate that.
And it would be the same answer for gravity is strong enough to hold the moon in orbit,
Yes.
but astronauts can float about and pretty much choose what direction they go in.
No. Astronauts are like, for astronauts to move, again, so space, let's assume it's empty. There are photons here. We know from Planck mission there are photons, but let's say, and there are particles, but let's say in the first approximation it's empty. So there is no buoyancy there. There's only gravity in space, yeah?
Our survey said.
And move on to your subject, exoplanets. What percentage surety do you have of there being other Earth-like planets? Are you 100%, or are you 80%, or are you 65%, or do you change each week?
I think we are 100% sure that there are planets like Earth out there.
Okay.
We are, say, I don't know what's the error bar, like say 80% sure that there are 30% of those planets
Habitable.
No, Earth-like.
Yeah.
That out of all planets in the galaxy, 30% are like Earth. This is our like estimate.
Yeah.
But we're 100% sure they're there. It's just the question now in this science: how many, and how close they are to the Earth. So that is the questions. But this question, if they're there, we already solved. It's there.
Okay. With these people I was speaking to, let's pick the TRAPPIST-1 system, the one that got into the media. This was the image, and I believe with photomy and other ways of measuring, I think you measure the brightness, the electromagnetic spectrum, and spectral changes. Then this turned into this colourful planets with volcanic activity, water content. How do changes in electromagnetic activity and spectral activity and brightness, such as the image in the bottom left, how does this turn into all this information about volcanoes and water and size and atmosphere?
These are just models. All these pretty pictures of exoplanets, they are all artist impressions.
Sure.
Yeah.
Do you think that's misleading to the public?
Yes, I do. It's pretty beautiful, and if you are not in the field, like a public, you look at this, it's like, wow, this
They found this.
Yeah, they found this, and it's absolutely misleading. I disagree with this, yes.
Do you think, you say it's 100% these planets exist, do you think it's a leap of faith to say, okay, I measured some electromagnetics, I measured some brightness changes, I got some spectral graphs of data. Do you think it's a leap of faith to say these are habitable Earth-like planets?
Well, it's still science. No, I don't think it's leap of faith completely. Yeah, so it's still science. Indeed, in astronomy, we just analyze mostly data and mostly electromagnetic. Right now, it's gravitational and particles, of course, but mostly it's electromagnetic waves. Yeah, and that light, electromagnetic waves, contain a lot of information. We learn about composition of the sun, not going there, because we analyze the light of the sun through spectroscopy, polarimetry, and so on. Yeah?
Sure.
So we do the same with stars, and we do the same with other planets. We see very little specks on our
which I've shown down here.
Yeah, exactly, on our detectors. But we can analyze this to get chemical composition, for sure, and we detect water, and we say, yes, look, there is a signature of water. We know that signature in the spectrum is water. So there is water.
How does that spectral information turn into water?
Because molecules in the atmosphere, for instance, in our atmosphere, there is molecules of water evaporating from the ocean. They specifically interact with the light coming from the sun. They absorb a certain...
So you're getting the same data?
Yeah, you get like imprint of molecular presence, because molecules are rotating and vibrating, and that requires energy for them. So for molecule to exist, it needs always absorb energy.
Okay. How can you be confident of the accuracy when you're trying to measure things 230 trillion miles away?
How what?
How can you be sure of the accuracy when you're going 232 trillion miles away with a little instrument on Earth?
Yeah, that is quite amazing, probably to understand. But this technique of spectroscopy is basically distance independent. If you see in print, of course, the problem is to collect enough photons. So when you go further away,
Light photons.
Yeah, light photons. You need to collect them enough in order to see the defect due to water absorption, what we call. And for that, for example, if defect is 10% relative to the total flux, then you need, let's say, at least 100 photons to detect it, you know? So that it depends on your detector. Let's say you need 10 photons would be probably not enough to detect it. You need more, maybe thousands of photons.
The more data, the more patterns you can
exactly.
get.
But it's really distant independent in this case. So if there is water, it doesn't matter is it here or 1,000 kilometers or in the lab.
So what would be your number one proof? You're at a dinner party, someone says, what's your number one proof, scientific method of Earth-like planets existing in the galaxy?
So far, we know they exist through transit techniques. This is our... these are not, like you have a curve there, this is not a direct detection of a planet, it's indirect. It means that the planet transits across the disk of the star and then we see this dip. This is not water, this is just a presence of a planet. And by amount, how big is this dip and how much it lasts, we can say whether it's small planet, big planet, on which orbit it is, you know. And through that, we know that there are these kind of small planets, yes.
Okay, great. I have a couple of questions about the moon. I'm sure this is just an error with NASA. This is a famous image called Earthrise, but there's a problem with it because the Earth's too small. Okay, moon viewed from Earth is this size, and Earth viewed from moon should be a lot bigger.
Well, moon size also changes through month and through years, because orbit of the
apogee, perigee.
Yes, orbit of the moon is not exactly circular.
Sure, but the Earth should still be a lot bigger than it is in that very famous image.
I didn't compare it, but we have to. I mean, in principle, one has to calculate what was exactly distance at that time of the picture, and then calculate the size of the Earth from that distance, angular, and then...
I've had some physicists do the maths on it, and they said it is a big error.
I see.
It's very interesting.
Yeah. Well, this is like to the stories, maybe they were not there.
This is interesting. Some people I know were measuring the moon. They're interested in space and the sky. The moon was photographed at the same time in Australia and Florida. How would that be? How's that possible?
Okay.
And this can be repeated in different sides of the globe, shall we say?
Yeah. Well, they are definitely upside down, so that
it's rotated.
Yes,
yeah.
You can. I mean, with respect to each other.
But the same phase.
Oh well, it's the same phase. Yes. Why should it be different? Because the phase of the moon depends on the sun.
Because one of these locations shouldn't be able to see it. So on the globe, say the moon's here in Florida, the guy in Queensland shouldn't really be able to see it.
But this is a full moon, close to the full moon.
Close to full moon.
So this means that there is an angle at which it's seen. So full moon means that the Earth,
opposite.
Yeah, the moon is opposite to the sun. Yeah.
But still, with the globe, with the Earth being a globe, it shouldn't be able to see them both at the same time. And this is being repeated. This is an anomaly that some people can't work out.
If somebody does it, so it's possible. For me, it's like this, you know. You cannot say me impossible if somebody does it.
Sure.
So then I say it's possible, and then you can ask why it is possible. Then I do calculations.
Yeah.
So I would say you cannot argue. If this is not a fake news.
I can verify this.
You know, if it's not a fake news,
yeah.
then you have to say, okay, interesting, it's possible. I would like to understand why, and then maybe it's possible only a few times a year. You know,
It could be done daily.
Daily, okay.
Even
then,
with
then
just
it's,
after new moon.
Then it's fine. You know, then it means that moon is far enough from Earth that in a full, close to the full moon, yeah, you can see it like from the front and from the edge.
But in the model, there's a model software called Celestia.
Yeah.
Yeah, you know Celestia?
I don't know. Yeah, there are many.
It's a mod. Yeah, there's many.
Yeah,
It's a 3D model of the solar
Yeah,
system.
yeah.
When you put this date and time in, you shouldn't be able to see the moon from both places. So there's a problem somewhere.
So probably model is wrong. I would say. This is for me, as a scientist, we're always like, okay, there's a puzzle, there's observation, which is true data, and there's a model which cannot confirm the data. Then I'm sorry, the model is wrong. So
you would say direct experience is the king.
yes,
I
absolutely.
agree with you.
Absolutely.
Yeah, I totally agree with you.
If this is possible, like you,
The data has to match
yeah,
the
then the model
observation.
is wrong. Then your program probably
Because that's science.
Yeah, exactly.